Welcome back to our video module on damp harmonic motion. Let's pick up where we left off. Now this gives us a little bit of a feel, but we want more than this. So we want to jump into this and figure this out on our own. So let's start off with our free body diagram. Our free body diagram for this is we'll have our mass with, of course, the vertical forces, the force of gravity, and our normal force. And as we already discussed, we want to keep the forces in tension. So we can do the force of the spring, and the green one we'll also put in the positive x direction would be the force damping, the damping force. And just as a reminder, we can keep our coordinate frame like this, x and y. Now that said, let's try and use our equations of motion. All right, we'll keep it like this, just so we can see what's happening. Now, I haven't told you yet what the damping force actually is. And in magnitude, or the amount of the damping force, we'll do this to make it really obvious, that's going to be proportional to the velocity, x dot, bx dot. And in fact, damping sometimes is usually modeled like this. Whether or not it goes like that in real life is a completely separate question. So now let's go ahead and write our equations of motion. Let's give ourselves as much space as we can so we can still see the model. The force of the spring, it's moving in the positive direction. Well, first, our sum of our forces equals m v dot. And the force of the spring equals negative kx. Now, how do I know that it's negative kx? Well, I know that it's either positive kx or negative kx simply because we've already learned that, where x is the deviation from the rest distance. If x goes positive, in other words, if the mass goes, say, over to the right, here we could even draw it right here, and we'll just we'll draw it in yellow. If the mass goes to the right and compresses the spring, which way is the force acting? It's acting to the left. That's in the negative direction. So we see that the force is acting in the opposite direction of the position. We've seen this before, so this shouldn't be a surprise, but it's always good to check. Now, we can do the same thing with the damping. What happens if the velocity, now we looked at position, yellow, what happens if the velocity is going to the right? Well, the dampening mechanism will fight that velocity. It'll push back. So in both cases, we see a negative in front of our force. Let's try and move this down a little bit. There we go. So that's negative kx, and the drag force is negative bx dot. Great. Now we can plug in these equations and see what we get. We have negative bx dot minus kx equals, and we're going to go back to mx double dot. Remember, we have a couple options. Now we're going to put this all on one side, and I'm going to drop the colors just because it makes it a little easier to write. Mx double dot plus bx plus kx equals 0. And with that, we're pretty much out of time. Join me in our next module as we continue our thinking and explore this a little bit more.